Great. Welcome, everybody. Hi, my name is Jennifer Griffith, and I work at the Northeast Waste Management Officials Association, which is an interstate association of the 8 Northeast states. So the 6 New England states and New York and New Jersey work together through NEWMOA. We focus on solid waste, hazardous waste, waste site cleanup, and pollution prevention and toxics use reduction efforts. So for waste site cleanup, one of the main priorities through NEWMOA is training, and that's what we're doing here today, sharing information about PFAS, which has been occupying a lot of NEWMOA and other people's time for the last eight or so years. So we have a great webinar today on a couple of emerging issues. But I'm starting here, I'm showing the NEWMOA website, right? Laura and Ian, you can see the website?
Yeah.
Okay, great. So I'm showing that because I wanted to let people know that this presentation the PDFs from the presentation will be posted later on the NEWMOA website. And I wanted to just show everybody where they will end up being, so you can find them, and also other things. So NEWMOA.org, and then we have events. The events are very forward focused, so it's all the events and the webinars that are coming. I have more than I'm organizing, but the ones that are posted and ready for registration are up here. But if you just click this back arrow here, you can go to past events. And so these are NEWMOA wide. So some of them are waste site cleanup. I've done other non-PFAS things. Then we've got other projects that are more solid waste focused. So there's a lot of things. We did a whole conference on PFAS back in April, and eventually all the presentations for that will be posted here as well. And then, you know, it's the backward ones are going forward. So all the way at the bottom after today will be the webinar that we're having today. This was the webinar we had a couple weeks ago. So with that, that's the NEWMOA website and where you'll be able to find the presentations eventually. Hopefully in the next couple weeks, Ian's going to send me his too. What else? There's a lot of people on the webinar today, so we will be just doing questions by typing them in. So everybody has a in your GoToWebinar control panel, there is a question box, so you can type questions in at any point. You do not have to type them. You don't have to wait until the official question time to type them in. And then I will be reading those. So we did also this time for these webinars apply for, and we were awarded Massachusetts licensed site professional continuing education credits for these webinars. So if people are on the webinar because they want and need those credits, so again, it's just Massachusetts licensed site professionals, not giving out other kinds of certificates. So just if you're a Massachusetts licensed site professional and you need the continuing ed credits, you need to be on the webinar the whole time. I can tell you GoToWebinar, whether you know it or not, knows if you're doing other things on your computer. So you need to have this webinar as your primary thing you're doing. You can't be checking emails or doing other things, or you will not, I will know, and you won't get a certificate. So we also had to insert some poll questions into the webinar. So those will be simple, easy poll questions, and but if you want the Massachusetts licensed site professional continuing ed credits, you must answer the questions. Doesn't really matter how you answer them, you just need to show that you're there and answering. Also, I do want everybody that wants a licensed site professional credit to ask a question, to type in a question, again showing that you're engaged in attending the webinar. So and then the last thing is you've got to email me at some point after the webinar to let me know, because I don't have any way of knowing whether you wanted the Massachusetts LSP credits or not. So please let me know that. So again, a reminder that the presentations will be posted eventually. First, I have to get them and then post them hopefully next week. And you can type in questions in the question box at any point. So I think with that, I am done with the logistical stuff. And I will, let's see, I have to turn over the presentation to Ian. And I will introduce him, and then I will mute myself and turn off my camera. So Ian Ross is the Global PFAS Practice Lead at CDM Smith, and he's a visiting professor. Oh, Ian, we're seeing some document of yours. So
yeah, I'm trying to get the correct screen to show. Let's just go to.
Okay. He moved from the UK to the US. He's currently in the San Francisco office of CDM Smith, and he's also a visiting professor at Manchester Metropolitan University. There we go, Ian. That's all set now. Ian has over 30 years experience in environmental impact of xenobiotics, so foreign substances, and has focused solely on PFAS management for the last 10 years in his global role. He's written over 100 articles, academic publications, and book chapters on PFAS, including the 204-page chapter on PFAS in the Emerging Contaminants Handbook. So we have a real expert here. So thank you, Ian. And like I said, I'm going to mute myself and turn off my camera, and you can take it away and turn off your camera too.
Thanks, Jennifer. Yeah, my camera's going off, so now you can just see the slides. So I'm going to run through ultrashort PFAS, which are becoming more of a concern in various parts of the world. I'm going to start off just by introducing PFAS again and talking a little bit about precursors, and then focus on ultrashorts, their fate and transport, how we can measure them, what they are, some of the issues with refrigerants leading to ultrashort PFAS being detected in rain, safer alternatives, a little bit on exposure and toxicology, although there's not a lot known about human toxicology, and then round it up with a summary of sort of where we are with ultrashorts. So really, PFAS as being, carbon's fully saturated with fluorine, first invented in 1890, and we see the first invention of a perfluoroalkyl acid was 1922 by Frederick Swartz in Belgium here. So this all predates the sort of discovery of PTFE by Roy Plunkett by many years. Trifluoroacetic acid, known to be extremely strong organic acid when it was first made, and we see trifluoroacetic acid precursors being developed and synthesized in bulk quantities, over 100 tons a year during the 1930s for military applications. And so these dyes, for example, are trifluoroacetic acid precursors here, which will have been used for many years before we think PFAS were first sort of developed and used in bulk quantities. So in terms of PFAS, 1949 is the first date I've seen where you've got evidence published showing there's biological recalcitrance. And this all predates EPA formation in 1970, Rachel Carson, Silent Spring in 1962, focused on DDT. Partly what reason DDT is recalcitrant is because it's got a halogenated carbon here as well. So PFAS comprise two major groups, as in the name, per and polyfluoroalkyl substances. The polyfluoroalkyl substances have a perfluoroalkyl group, which is this green part here, where we have multiple fluorines saturating a carbon backbone. But then attached to that, we have additional functional groups that maybe make it a slightly better surfactant, for example. But the rest of this molecule will be transformed away over time. Microbes will want to attack this and take these white protons off here. So polyfluoroalkyl substances are generally precursors to perfluoroalkyl substances, which are the species that then persist indefinitely in the environment, where we see soil and groundwater. We're not seeing certain microbes that can attack these molecules at abiotic reactions. And for some of these chemicals like PFOS, it was pretty clear from the 1950s, if you're using it in a chrome plating bath, you've got a very oxidizing environment which should break down organics, and PFOS survived. So these are the species which we're seeing really being more regulated at the moment, but often the precursors are what's actually in the products that are used, and this can be helpful with forensics. So to try and explain this more simplistic, we see precursors as more like an arrow that was shot in a battle. Say we're in 6000 BC in northern Africa, where we find stone arrowheads that are dated for thousands of years old. We don't find the whole arrow. We found just the arrowhead. So if you think of this molecule as an arrow where part of it's made of wood and it degrades away, it leaves a stone component which looks like it's going to persist indefinitely. And we see this is what we'll find. So this is a precursor that's found in firefighting foam, and this transforms in the environment to form PFOA, which then persists indefinitely. So these molecules by sort of European standards are also classed as being persistent because they transform into persistent daughter products. And the same is true with the ultrashorts that we'll dive into. But really, we're seeing a broad spectrum of PFAS, as has been coined a term in California, where a lot of the molecules that are precursors are put in a dark area of this rainbow, where we see molecules like these dipaps that transform to make PFOA or PFHXA. And we move through, like we've got long chain, we've got replacement fluoroalkyl ethers, we've got oxygen in, cyclic PFAS. Then the short chains, generally down to C4, C6, C7. But ultrashorts go lower. So we're like C1 to C3, exactly the same structure, just shorter carbon chains. So what it means is essentially there's a lot of differences in their behavior. So as we go down the chain length, solubility rises massively. They get more hydrophobic and they stick to the fractional organic carbon. They'll stick in the ground if they get to be longer chains. And then C8 is sort of the optimal perfluoroalkyl chain for a surfactant. But you can still get some surfactancy down to C4. Well, C4 butanoic acid, C4 butyric acid. So PFBS is a surfactant, but PFBA is not. Then we classically looked at bioaccumulation of PFAS in fauna. So we look in animal species and fish. And these are the longer chains. So things like PFHXS is long chain, and basically PFOA here is long chain for the carboxylates. But as we look at sort of the accumulation or the concentration of PFAS in plants, that's more pronounced when we get to these shorter chains. But usually these bioaccumulation factors are pretty low in comparison to what is used by regulators. Usually to be bioaccumulative, you need a chemical to bioconcentrate up by a factor of 5,000. And usually it's a lot lower in plants. It's more like 40-fold for some of these short chains. But as I'll show, it's much higher for some of these ultra shorts in plants. So we're focused on these ultra shorts at the moment. You could say equivalently as persistent as the rest of the PFAS, but far more mobile, far more widespread, and far more uses of them. So the ultra shorts have over 1 million precursors. So that means synthetic chemicals that have been generated that are going to transform naturally in the environment to lead to the formation of things like trifluoroacetic acid as a terminal product, which seems to persist indefinitely. These can come from fluorinated refrigerants, and some of the reviews that were done like 20 years ago, 25 years ago by Bortonay, really reflecting as we phased out chlorofluorocarbons to assist with sort of ozone depletion, we moved to some specific alternative refrigerants, and they were proposing that we end up with about 155,000 tons of trifluoroacetic acid in rain each year coming down on the planet from just a couple of these replacement refrigerants. And now there's more refrigerant replacements coming out that potentially add to this. So around the world, we're seeing an increase in these precursors, in TFA detection specifically, and that could come from multiple different precursors. It could come from deposition from rain as well. But we're certainly seeing increases in blood as well, with the Chinese blood up to 8.5 micrograms per liter as a median, when TFA is not a naturally occurring compound. In terms of what we're seeing out in the environment is a xenobiotic. So the other point here is it's usually pretty high concentration, and it will go through activated carbon, and ion exchange resins are designed to remove these PFAS. So there will be exposure, even if there's an attempt to clean up the PFAS we're focused on from regulatory sort of attention at the moment. We're moving into these PFAS moving through the common treatment methods that are used to clean up drinking water. So some of the example publications coming out recently, this one by NEWMOA was just making a point that if you look at the mass of PFAS in German drinking water, 98% of the mass is forming these ultra-short molecules, TFA, PFPRA, and TFMS. They only looked at 43 samples. Germany had set a drinking water standard at 60 ppb with a target at 10, but 3 out of these 43 samples exceeded the 10 ppb. Then we've seen Germany sort of now sort of proposing this level, but the Dutch and the Danish are bringing drinking water standards down lower. So the Danish standard was 9 ppb as the actual standard, not 60 ppb here. And RIVM in the Netherlands has just brought out a standard of 2.2 ppb as well. So we're nowhere near the PPT levels that are for the long chains, but still, if that's a safe level, are we seeing significant exposure? So this study from Indiana was focused in on trifluoroacetic acid levels and the other short chain lengths, long and short, in dust, drinking water, human serum, and urine. And the bottom line with this was, 92% of the mass in drinking water is coming from ultra shorts. In human serum, that contributes to 66% of the mass of exposure. Short chains, only at 7.2% and 3%. But with the longer chains, I think we are currently regulating, 1% of the contribution in drinking water, but 31% in plasma. So there is a, when you've got something that's bioaccumulative in humans, you would expect to see, less of it in water means more exposure in serum. But then the point is there's far more ultra shorts around than anything else. So 2/3 of the exposure is coming from them. Then there are many precursors out there. Just been showing on this one really that we see these refrigerants, this replacement for CFCs and HFCs transforms in the atmosphere to form TFA, so that will come down in rain. And as we see these types of refrigerants here, we also see various agrochemicals being used, which have a perfluoroalkyl group on them, like a CF3 adjacent to other functional groups, meaning they will transform in the environment to form trifluoroacetic acid. These are the dyes used by the German military in World War II in the early 1930s, so 100-ton quantities used, and also there's some ultra shorts in firefighting foams. I think there are more impurities really there. But just to say, we have a lot of synthetic molecules out there in the environment that will eventually transform into form trifluoroacetic acid, and that includes pharmaceuticals like Prozac here. But it's obviously the rest of this molecule will eventually biodegrade and leaving TFA. So refrigerants are more of a focus in Germany, and really looking at the concern for refrigerants being used and then deposition in rain as a major source of TFA, which then means TFA is going to get into surface waters, crops, etc. But this has been ongoing since CFCs were restricted. So we're looking at a sort of 25-year history of use of these molecules. Some modeling done across the states is showing sort of Nevada, they're predicting, and California, maybe up to as high as 8 ppb of TFA in rain. But the measured concentrations that we've seen published so far from some of this work done by Worcester College and Paul Edmiston's lab, revealing what's in rain across the states for PFOA, PFOS. I mean, the maximum for PFOA was 50. The maximum for PFOA was 30 ppt. But we see a range here. There's usually some kind of detection. But when they also look at trifluoroacetic acid, where up at ppb levels, that's sort of 1.2 ppb, 1200 ppt here. So a lot more of these ultra shorts coming down in rain, and that's been ongoing for a few decades now. So this means we've got an ambient background of ultra shorts out there, and they're going to be higher than what we see for other PFAS. We have volatile ultra short precursors as we do have for other chain lengths, but basically we're seeing widespread distribution of PFAS, be that long, short, or ultra short. It's just the ultra shorts seem to be present at a far higher concentration, normally 100-fold higher than the other PFAS. In terms of chemical analysis, this has really moved into the commercial sphere in the last 3 years, where we now see major labs offering ultra short analytical methods as standard on their suite of PFAS. So this is certainly meaning there's more potential to look for PFAS, and I know in California they're doing a study of ultrashort PFAS across the state. I think some of the information out there is sort of coming from very old publications which have now been superseded, claiming that TFA is naturally occurring. And I would point people towards this article by Shira Judan and her team looking at the insufficient evidence for really proving that there's any naturally occurring trifluoroacetic acid. It seems that really, when you consider all the precursors out there, that accounts for why we see so much TFA out there, and there's no real solid evidence that it's coming out of any volcanic emissions. So the refrigerants that we've seen, we're moving from different acronyms, hydrofluorocarbons, hydrochlorofluorocarbons, and hydrofluoroolefins now. With hydrochlorofluoroolefins, but they're used commonly in air conditioning systems in vehicles, especially as we've moved away to things like we're using this HFO 1234YF as a replacement because of lower global warming potential. But we also see an increased potential to form TFA. So these HFCs or HFOs transform in the environment via attack via like hydroxyl radical, UV light, etc., hitting certain molecules that will mean you end up with a terminal product coming down in rain in the form of trifluoroacetic acid. So taking some of Atmo's slides here, these really showing that as we moved through the years, we started off with CFCs and they had an ozone depleting potential up here where it phased out. And we started looking at global warming potential for some of the HFCs. And then they were phased out, and now we're moving into some of the HFOs, which if we look at some of these like the 1234YF, the HFO here, 100% of that in the atmosphere converts to trifluoroacetic acid, which comes back down in rain. So another sort of environmental issue as we move from one alternative to another. But they're pointing out that here at the bottom, we've been using molecules like propane, isobutane, ammonia, etc., CO2 for refrigeration since the 1830s, and these have no deleterious effects when we're looking at the potential for them to be remaining in rainfall, getting into groundwater, drinking water, or global warming potential, or ozone depleting potential. So the fact that many of these can be used is now a factor of really engineering them into refrigeration systems. Just pointing out that we're back to where we started in 1830s with the molecules we were using for refrigeration. We've gone through CFCs, HFCs, HFOs, and now really recognizing that organofluorines in refrigeration systems will lead to some form of deleterious effect on the environment, be that it's going to get into your drinking water or it's going to cause global warming. So when we look at the impact of ultrashorts, I think, less is known about the toxicology, but the route to exposure, I should say, is one of the concerns. And that comes down to, Bortonay in 1999 was mentioning, plants, including wheat and sunflowers, can concentrate up these ultrashorts. And more recent publications by Zhang here is just showing by how much. So in the roots of wheat, we see over 1600-fold concentration of TFA. We would expect to see a little bit of PFOS here, as that is known to accumulate in more in the roots of crops, but the edible portion of the crops is often more where we're concerned. So wheat is showing here, it's about nearly 1100-fold increase in concentration. And so there's a question on exposure from various plant products, and this is where European Food Safety Agency is focused as well, but more on the molecules that are added to plants or basically used as pesticides. So food and drinking water is considered to be a major contributor to human exposure and other organisms' exposure. But EFSA is saying that they're more concerned that some plant protection products, which I showed before, are more likely to cause exposure to trifluoroacetic acid. So these molecules here that are used as pesticides that transform into TFA are also a concern that they may be adding more exposure to human population than what's in drinking water. In terms of toxicology, most of the studies have been done on organisms like rats, guinea pigs, but at very high levels. So you can't really compare them to humans that easily, and the concentrations applied are very high. We've seen, for example, NOALs in rabbits at 160 milligram per kilogram per day, so pretty high concentrations. And recent publications by Decant over here basically making the point that there's probably a 100-fold margin of safety or margin of exposure to current levels of TFA. But we are seeing drinking water standards going down and some exceedances of drinking water standards in Europe. The most recent work that the German Federal Office of Chemicals has been sort of working on is looking at the potential impact of higher concentrations of TFA, like 0.1 to 0.3%, linked to human reproductive toxicity. And those publications aren't yet out. We're in contact with the regulators, and they're just putting forward data to reach at the moment. So really, we've got high concentrations of ultrashorts that have been used for many years, continue to be used, but the toxicology is very little studied, let's say, so far. And so the main concern is, yeah, we've got a lot of exposure, but we don't really know the effect of that on us. So when we look at regulations internationally, I was trying to make a graph showing you where we're going on here, bringing concentrations down and adding in the RIVM target here. I mean, in Europe, we're seeing the sum of 20 PFAS, that's C4 above, below 100 nanograms per litre in drinking water. And they propose the sum of all PFAS below 500 ppt, but there isn't a method that's sort of agreed on how you measure this. And if you look at the trifluoroacetic acid and the other ultrashorts, often they would exceed this standard anyway. So in Germany, yeah, as I said, there's a two-tier drinking water standard, 10 and 60 ppb. Denmark went to 9, and yeah, with the Netherlands just reducing this to 2.2 ppb, this could mean potentially more sort of exposure above what's considered safe in the Netherlands. The lowest levels for PFAS in the world, considering the 4 bioaccumulative ones here, is Denmark 2 ppt for the combination of them, which is lower than what the US has proposed at 4 ppt for PFOS, PFOA, and the hazard index. So in the UK, yeah, we're seeing they're focused on 47, soon to be 48 PFAS individually, which all have to be below 100 ppt. I think what's interesting now is specifically Canada and California, which is saying, yeah, the sum of 29 PFAS here is proposed to be below 30 ppt. But that's not based on toxicology, that's based upon the performance of a treatment system to remove them. And California is moving in the same direction by talking about a broad spectrum of PFAS with treatment-based goals. So trying to remove as many PFAS as you can with technologies that are available. So as we move forward with all of this, it's going to be, I think, the cost versus the benefit really has to be studied. And yeah, I mean, the ultra-short chains are regulated at a similar level as the short chains at the moment, if we consider what the Dutch are doing here compared to where US EPA has gone on PFAS. So some of the concerns are, yeah, the PFAS that are the standard things we're looking for, like PFOS, PFOA, are coming down as in human serum as the production ceased and there's less use, but the total fluorine is going down a bit, but then there's more concern over what's going up and characterizing what's in here, and are we seeing TFA as part of this, or some, you know, fluorinated pharmaceuticals. So we are phasing some PFAS out, replacing them with others, but we don't really understand what's happening there with them. Replacement molecules also now seemingly going up in Chinese blood as well, like some metal placing replacements that are seemingly, you know, becoming a larger component of what's actually out there in human blood. So California Water Boards has been out doing an initial study of the total amount of PFAS using combustion ion chromatography to pick up all the organofluorines, and found, yeah, these blue bars seem to indicate significantly more mass out there. In terms of TFA, they were finding that you can saturate this carbon cartridge at about 1 ppb, so you can detect TFA with this total organic fluorine, like US EPA 1621 method AOF. But above 1 ppb, the carbon would become saturated. So you're not going to get a good estimate above that concentration, but still it is being taken out by. So this could partly explain what we're seeing here, where we see a lot more PFAS being detected using this total organic fluorine method versus all of the standard methods with target analytes. And, you know, internationally, California's brought in these regulations on developing standard operating procedures to validate a broad spectrum test for PFAS, and then develop treatment-based regulations. That's now a couple of years old. And European Chemicals Agency is looking at trying to restrict all PFAS, but you've got to really look at essential uses and alternatives, and the commercial use of a widespread number of PFAS. So California is going out to 4,000 drinking water supply wells looking for AOF, and I think it's a 533 suite, and 700 of those they're also going in to look for ultrashorts and do high-res mass spectrometry to work out if they can actually detect what's really there in terms of the PFAS content, to give you a better understanding of the range of PFAS that are in drinking water. So the poll question is, what chain length are ultrashorts, to keep it reasonably simple? And you've got A, B, C, and D. Are they C1 to C3, C3 to C6, C5 to C9, or C9 to C11? And with that, I think I'll just try and sum this up. These represent the greatest human exposure to PFAS. They're the highest concentration out there. We have less understanding of their toxicology. There are many ultrashort precursors. Are they in essential uses? They're not retained by activated carbon, and ion exchange resins aren't really designed to remove them from water. And regulations are evolving quickly, especially in Europe. I'd say there's just more articles coming out here on ultrashorts. And so.
And hold on. So people can only see the poll question, and it says answer Ian's question. So that's what are the ultrashorts? And then there was choice A, B, C, and D. Can you just say those again? And then most people have voted, I think, by this point. But
yeah, it's on the screen, hopefully again. A, C1 to C3, B, C3 to C6, C, C5 to C9, D, C9 to C11.
Okay, so we'll let people just vote for another 5 seconds here. If you want the mass LSP credits, you really have to vote, but doesn't really matter what you say. So, okay, I think everybody knows the answer to that one. So I'm going to close that one. And now, Ian, we'll see, you mentioned you were talking about something else. So go ahead and repeat that again. There we go.
Yeah, so the summary, if we look at all the PFAS out there, that it seems like the greatest exposure is from these ultrashorts, as they're present at higher concentrations than everything else we're detecting at the moment. I'd say the toxicological understanding of their impact is certainly developing, and the fact that they're accumulating in the edible portion of crops by over 1,000-fold may be of concern. There's a question as to whether some of these ultrashort precursors are in essential uses. And especially when we look at refrigerants, there could be some natural alternatives that could be engineered to be effective. When we're putting on treatment systems to take out things like PFOS, PFOA with activated carbon, they will not work particularly effectively for ultrashorts at all. And the same with ion exchange resins, they're not really designed for ultrashorts. So we may be treating a small proportion of the PFAS that are there that are currently regulated versus letting the bulk of the ultrashorts through. But then what's a safe concentration for PFAS in drinking water for the ultrashorts? And what the Dutch are saying at the moment is 2.2 ppb, which is significantly higher than the 4 ppt US EPA has proposed for the longer chains. And I'd say, yeah, regulations are evolving quickly in Germany, the Netherlands, Denmark, and across Europe, especially more focus in the UK as well on ultrashort PFAS and the sort of ubiquitous nature of TFA and how much is already in there and going into drinking water and associated with crops.
Oh my goodness.
That's a summary, I think, and that's my contact details, but I'll leave it on the summary there.
Great. Well, a bunch of questions have come in, and yeah, so I'll just start in on them. So right there, your fourth bullet, they're not retained by GAC and very poorly retained by resin. So what do people do? Is there some treatment? Is there a way to get it out of the environment and out of our drinking water?
Yeah, so you would expect reverse osmosis and nanofiltration to be effective. So definitely, reverse osmosis, as they're charged species, they would be removed from solution, and that would be a way of getting them out of drinking water.
Okay, so really those high cost efforts with reverse osmosis. Okay.
That's not the cheapest way to work, but you can get under sink reverse osmosis units for a few $100 if you have your own personal drinking water.
Yeah.
I mean, to be honest, it's also when you look at exposure from ingestion of crops and certain food sources, you may be very difficult to avoid exposure to them.
Which is another question. So
Yeah.
you showed wheat and a study with wheat, but are there studies of other crops and other food items, or?
I can have a look for them, but at this point in time, we've got a student working on this. So we're reviewing everything and pulling a summary of all of this together. So if someone wants to email, I can send you what we've got.
Okay.
I don't know the depth of the studies in plants at the moment.
Right. Right, with the ultrashorts. So how about rainfall data? Is it influenced by nearby sources, or because it's all precursor? I mean, it's precursor transformation. I don't know. Is it related to industrial sources, or like how do we know what background is?
I think there's more coming down in rain in the vicinity of urbanized areas where you have more potential for refrigeration systems to leak. So that seems to be what this modeling I had on the screen earlier was showing, was more you start to see, where you've got more populations on the coast here, there's potentially more in rain, but it's obviously going to depend upon atmospheric conditions, dominant wind flow, and precipitation events.
Okay. Here, could Ian please confirm again that if AOF, so that's what does the A stand for? Something organic fluorine.
Yeah. So
is
absorbable organic fluorine. Yeah.
Absorbable organic fluorine is less than 1 ppb, then method 1633 can also detect TFA. Is that true or not?
I think what they meant to say is 1621, because 1633 is 40 analytes, which doesn't have ultrashorts on it. 1621 is the combustion ion chromatography, absorbable organic fluorine, sort of AOF method. The feedback I've had from California water boards on this is they've run calibration curves, and below 1 ppb, they seem to be able to quantify trifluoroacetic acid and the ultrashorts with AOF. But when you go higher, it sort of saturates the carbon cartridge. And if you've got 5 ppb, it'll only report it as 1 ppb. That's the logic.
Okay. Okay, so is that the basic way for the analytical method? Like what other, are there other analytical methods that you could use?
You can go to the major commercial labs now and just request a specific method for ultrashorts. So, I mean, Eurofins, SGS, ALS, others around the world have got methods already available. We're using them with top assay at the moment to see how many ultrashort precursors are on some sites. So, yeah, you can specifically ask for a chemical analytical method that'll give you the exact concentration of each one of these analytes, as opposed to relying on AOF.
Okay, here's a question or a comment that I was thinking too. So, we started using HFCs and CFCs because they were safer than those natural refrigerants. So, yeah, is there active movement towards going back to them? And do we think that there's going to be ways to overcome the safety concerns, or?
Yeah, I mean, I'd put the analogy in that we wanted to prevent exposure to chromium in chrome plating baths, so we put a PFAS blanket over the top. So I think we replace one thing with another that has unforeseen future consequences. And yeah, the ATMO team are certainly working on promoting the fact that for the vast majority of refrigeration systems, you can now engineer in a natural refrigerant. There's no need for anything halogenated like a fluorocarbon or chlorocarbon here. And it's more that you can't easily retrofit. So you can't go to an existing refrigeration system and say, oh, we just want to put propane or CO2 into this one. They need to be designed around CO2 or propane, isobutane. So for new builds and for automotive manufacturers, they could be switching to natural alternatives and avoiding the use of anything that causes PFAS in your drinking water, say, which is where we're going at the moment with this 1234YF.
So do you feel like people are aware of this enough in that manufacturing world that there's a movement to move that way? There's momentum?
I don't think so, no. I think there's awareness, but I don't know how easy it's going to be. The recent conversations I've had with this, because I know a green science policy had been to see some motor manufacturers, and yeah, there's certainly awareness, but how easy it is to switch over a car's refrigeration system is another thing.
Okay. So there's several questions about California and their regulations or their policy moves. And since you're now located there, maybe can you provide more information about their treatment-based goals and where that's going? And what else did someone ask about? There's other.
California are in a sort of phase of examining the massive PFAS that is across the state, with the objective of characterizing it using multiple different types of chemical analysis, and then working out, well, what treatment techniques could we use to remove the bulk of these PFAS or specific PFAS within here that we find. But in terms of specific regulations, I think they are still focused on a specific molecule being removed. But their objective is to try and remove the entire class as best as possible, but that depends upon the performance of the treatment technologies, and there's a potential for them to be doing a lot more trials on treatment of multiple types of PFAS with different technologies over the next few years.
Okay. So let's see, we'll take maybe one or two more questions. So the detection limits. So longer chains, we've got really low detection limits. But what about the ultra shorts? Can they also go down to low levels or?
No, not at the moment. I mean, what I'm getting from one lab here is trifluoroacetic acid is 400 ppt, but usually you're finding it higher than that, I'd say, in many places. So if the regulatory standards are sort of 2.2 ppb in the Netherlands, then yeah, this is lower than that. So they're not as low as the PPT levels that we see for long chain at the moment. But do they need to be? Because the regulatory thresholds for what's safe is much higher.
Okay, now sort of a comment question about just some areas don't get a lot of rainfall, so do they have lower levels, and do the people living there have lower levels? And then a related question I have is, does it retain in the soil, or is it pretty much just go right, if rainfall just goes right through and into the groundwater?
So I don't think anyone knows predominantly if a certain population has higher exposure as a result of rainfall. But if European Food Safety Agency is saying they think these types of pesticides give you more exposure from crops, it depends where these are used. And these pesticides, yeah, they will transform in the soil to eventually lead to trifluoroacetic acid, which should be very mobile. These may be sticking to soil far more than trifluoroacetic acid, which would eventually go to the aquifer below. So yeah, I'd be more concerned about multiple sources, not just rainfall, but the products we're using as pesticides.
Okay, two people want your opinion. So two questions, and then we got to move on here to Laura's presentation. But what's your opinion on thermal destruction of PFAS and of these ultra shorts? Is thermal feasible? What do you think?
Yeah, I mean, there's a study of incineration that's starting with US DoD, US EPA, and Clean Harbors and others to really review combustion byproducts coming out of incinerators using these OTM 45, 50, and 55 methods that US EPA has just developed. So I think once that's done, we'll have far more confidence with thermal approaches and incineration. Effectively, what we're seeing at the moment is to stop production of things like carbon tetrafluoride and hexafluoroethane from incineration. You would need 1400 degrees C or some kind of capture system. But then on the other side of this, yeah, thermal, when you add calcium, you can get effective treatment at lower temperatures. So we're certainly seeing the addition of calcium, which ends up forming like a calcium fluoride as the original mineral that we started getting PFAS from, the fluorspar, can mean thermal can be far more effective. So there are some like thermal methods out there for treating soil where you're adding calcium, which look like they're going to work at lower temperatures.
Okay, one more. What's your opinion about the ECOS? So that's the Environmental Council of States. So that's like this commissioner level national association resolution being proposed that they're want the EPA to use a definition or classification scheme for PFAS that only requires only one single fluorinated carbon for it to be a PFAS. What's your opinion of that?
That would fit in with what OECD is saying, and I know California is falling in line with what OECD are saying, and it would fit in with the UK trying to classify PFAS on the basis of their extreme persistence. I don't see any logic with the US EPA saying you need to have 2 perfluoroalkyl carbons in a molecule to make it a PFAS. Yeah, I can just say, from a logical perspective, you've got 2 molecules next to each other which are equally persistent. Why is one ultrashort a PFAS and one isn't? Because that, under US EPA, that would be a PFAS, but this wouldn't. And they both are extremely persistent and mobile. So why would you say that's not one? I don't understand that.
All right. Great. All right. Well, thank you so much, Ian. But we're going to move on now. We can answer some more questions at the end if there's time here. But I'm going to turn it over now to our other presenter, Laura Trozzolo, who is, let's see, everything just went away. Who is with TRC Companies. She leads TRC's risk-based modeling. Oh, did I make you the presenter? I didn't do that yet, did I? Oops, yes, I did. Okay. So she leads TRC's risk-based modeling and risk assessment practice. She is out of their Fort Collins, Colorado office. In this role, she provides technical and regulatory oversight for a multitude of TRC projects and leads the company's risk assessment center of research and expertise, their core team, while supporting professional development of TRC's risk assessment staff. She's been with TRC for 10 years. And she's got 29 years of experience in human health risk assessment and risk management on a multitude of sites. So also another very knowledgeable person here to talk to us about the vapor intrusion, but I'm not seeing your screen, Laura.
Uh-oh, okay, there we go. How's that? Can you see that now? Is it a slide? Sure. How's that?
There we go. There we go.
Okay.
All right. So
do you
before
see my presentation?
Yes, we can see your presentation, okay. But before you start, we have to do another silly poll question here. So where does Laura work? Please select one. US EPA, Tetra Tech, TRC Companies, or CDM Smith. Please do the quick poll. And we'll just wait.
So I can, whenever you're ready, I'll just jump right in.
Yeah, so just we'll give another 10 seconds or so. And then I will turn my camera off and mute myself and you can take over. So anyone else need to answer? And okay, I'm gonna close that and turn myself off and mute myself. Take it away, Laura.
All right, thanks so much. Well, Ian, I'm pretty intimidated because that was like a whole 5 hours of PFAS information. So hopefully people have a little more brain capacity to take in my presentation. So yeah, today I again, as Jennifer mentioned, I'm a risk assessor. So what that means is, we deal with everything across the board. And when PFAS came into the realm of the practitioner of us looking at PFAS, one of the things that people ask me all the time, because I also have been doing VI work for about 20 years, or vapor intrusion work, people ask me this all the time. What's going on in the world of vapor intrusion? Because this is obviously it's an emerging contaminant, it's an emerging scenario. So what are we going to do here? So basically, this is just more of a practical guide, not just to VI or vapor intrusion, but to really talk about some of the issues that Ian is talking about, where we're looking at deposition, precursors, things like that. So some of this is probably going to be repeat information, but again, this is and it's not as data intensive, but just more kind of like I said, a practical guide. So with that, I will begin. Oops, there we go. So just a couple of things on my overview. In the world of risk assessment, we look at source and migration. How does something migrate into, a media? And then ultimately, how are we exposed to it? And looking at it from both a worker exposure and a residential exposure. And this, I'm going to broaden it out from just VI or indoor air, but ambient air and things like that. Some of the things going on with toxicology, I do a little like how EPA's RSL table has every 6 months they put out new toxicity, or they put out a new RSL table, and what are the things there we're seeing currently with PFAS and toxicology. And then just some occupational studies and what's going on with dust and air. So with that, I'm just gonna, obviously, if you read a newspaper or you listen to the news or a magazine, you see this everywhere, right? We obviously, Ian mentioned this, in almost every product you can think of, consumer products, in our drinking water, in medical supplies, in our toilet paper, not our toilet paper. So we definitely have an issue with it in pretty much, it's a ubiquitous substance. Some just quick, snapshot of some PFAS sources. Some of the things that we know kind of was the initial trigger is these firefighting foams, the AFFF. And then you think about who uses AFFF or who is using these firefighting foams, and that's anybody who might have a potential for fire. And so we've got oil and gas industry, we've got all these other industries as well. But then how does that affect me as a consumer? Well, we've got our textiles and leather and apparel and plastics and our contact lenses, and when you're having surgery, some of the surgical implements and things that are being used also contain PFAS. So really it's everywhere, as we mentioned that before. This is just kind of, again, another way of looking at where our PFAS sources. So pretty much, this is everything you can think of, or everything I could think of. But again, there might be more. One of the things that we just started talking about at the very bottom here, I have residential areas with septic systems. And one of the things that is becoming a kind of a more of a concern, or a theoretical concern, is when you have a house and you have septic systems that are just doing their job, but you've got household PFAS products, and then now they're entering into the septic leach field, and which is close to your house. Do you have any potential VI concerns? So something kind of to think about. So again, that's from the subsurface, but above ground, when it comes to PFAS in our indoor environments, really there's, again, our host of, bring home your fast food, go to the grocery store, you've got, you know, bags that you're using, or maybe there's food is being wrapped into something. You go, it's back to school here in Colorado, so lots of, you know, new backpacks and things that are resistant to stains and, you know, all of these consumer products, right? So one of the things that I wanted to talk about, this is a study that was done back in 2021. It has just basically a diagram where the fluorotelmer alcohols, or FTOHs, what they're finding is it's kind of the dominant PFAS in both ambient and indoor air. A lot of that might have to do with the fact that these are the lighter chains. They're more volatile than the heavier chains, and they're typically more persistent in the consumer products. So now that we've talked a little bit about the source, let's talk a little bit about migration. And migration just depends on what is the source and where is it being, you know, entering into the environment. So we have this industrial site example. It's from the ITRC PFAS guidance. I was fortunate enough to be on the team and was able to actually craft this, the CSM here, actually for all three of the sources in the document. But this just illustrates you have stack emissions. Those stack emissions could be either from you're actually making PFAS as a compound, or you might be, you know, putting it onto a product. So you're baking it onto something, and you're baking it at high temperatures. So you're going to get these stack emissions that, you know, depending on the temperature, the stack, the molecules will be, you know, very excited and want to go quite a bit up into the atmosphere. And there's other PFAS sources as well, or migration. You might have, you know, landfills over time, wastewater treatment plants, incinerators, and AFFF releases. But again, for this particular example, it's showing, you know, once it's up in the air, you've got air transport, which can, you know, be within the air shed, you know, immediately. But if you have, let's say, something that is fairly volatile, like a fluorotelmer alcohol, it could certainly become part of the long-range transport, which is a concern because we're seeing PFAS in, basically it's ubiquitous. We're seeing it in polar bear meat. We're seeing it in you know, everywhere on the globe. But so what I was just going to do is kind of dive in a little bit and talk about the nuts and bolts of atmospheric emissions. And again, it's more of just an informational, you know, topic here. So really, when you think about emissions, you're going to be either looking at particles or vapors. So the particles are things that are dominated by your anionic PFAS. PFOA and PFAS are typically the sort of hallmark chemicals there. And typically, you know, there's others, but I just wanted to give a couple of examples. So for example, the PFOA tends to absorb to smaller particles, while PFAS tends to absorb to the larger particles. But then again, what I was mentioning, vapor intrusion, anything that has to do with, you know, vapor, we're seeing is dominated by these neutral fluorotelmer alcohols. Again, those are the things that are in some of these consumer products that are, again, getting out into the atmosphere at high temperatures out of stacks and then being transported through the atmosphere. Therefore, not a surprise, you're seeing FTOH vapors. They're the dominant PFAS in ambient air. Typically, you'll see higher concentrations, as Ian was mentioning, over urban areas, but, you know, also seeing it in open oceans and remote areas as well. So transformation, this is something Ian mentioned as well. There's transformation that occurs. So you have these fluorotelmer alcohols. What happens is they transform into the terminal PFAS, basically the PFOA, PFNA, PFAS, and others. This is just again an example. And how does that happen? Transformation occurs through indirect photolysis and oxidation. by hydroxyl radicals. So kind of what Ian was mentioning in his talk with the arrowhead, which I thought was such a really cool visual, and I will remember that. But yeah, that the transformation is going is basically taking off the things that are not the terminal per fluoral, meaning carbon and a fluorine bonded. But the kind of, it's insidious in that the reaction rates can be slow, and then transformation, you know, it can be up in, if you're in a volatile, up in the upper atmosphere, you could have long range transport that you can have a volatile up in the atmosphere for weeks. So that's what is allowing this extremely remote, you know, exposure, deposition, and things like that, which I think we've all kind of heard and has been documented. So the last piece of this is the deposition. What goes up must come down. Not a surprise. Things that are particle bound are going to be a little bit heavier. They might fall a little bit faster than a vapor, which is by nature wanting to be up in the atmosphere. But you're going to see particle bound deposition through, you know, precipitation, rain, snow, or just maybe deposits, or, you know, it falls to the ground on its own. But when it comes to the vapors, things can, you know, it can actually fall or partition into the water droplet or onto the water droplet, and then just fall as rain or snow. So again, this is just sort of like the cycle to get to where we see anything that might be airborne, what happens while it's being, you know, migrating in the atmosphere, and then as it deposits. So this is just a graphic. It's from New Hampshire Department of Environmental Services, and it just really shows that the deposition accumulates over time. And so every year you get in kind of another layer and another layer and another layer. So that can create seeps. It could create a sink of PFAS that could ultimately then, you know, leach into groundwater, run off into surface water, and yeah. But again, these are all kind of concepts that we understand or have, you know, learned over the last few years. So let's see, I think the routes of exposure, this is sort of that same conceptual site model that I was just showing that was talking about the source. And now we're going to come back and think about exposure. So, you know, you've got inhalation once it's airborne, inhalation of airborne particulates and vapors. You might come into contact with the particulates as dust once they settle out of the atmosphere. And then, as I mentioned, leaching of something that's fallen into groundwater, and then surface water runoff. But I mentioned a little bit earlier about the surface release related to septic systems. So this is just a diagram that I put together just to show a visual. So you've got, you know, basically a leach, which could very well just be, you know, they're perforated pipes, which allows the leachate to go back out into the leach field. So you've got leachate migration, and once it's sort of, you know, gravity, it's going to go down into groundwater and migrate down gradient, whatever direction that is. But it can also volatilize up into, you know, it become vapor, and could potentially become a VI concern through the, you know, migration of indoor air, which you would ultimately, you know, if whether that's a house or a building, any kind of a building. But again, the septic system is typically, you know, tied, you think about residential areas. So you are the consumer, and then the PFAS becomes, you know, part of the problem. So it's almost like a cyclical problem. There's some other, you know, exposure pathways that are related to this too, where you're impacting groundwater. So you might ingest the drinking water if you had a groundwater well. There might be some groundwater transport that would ultimately partition into surface water, such as a lake or a stream, and then you're going to have ecological concerns from fish uptake from impacted surface water or sediments. or eating the fish, going out and eating. So you as the consumer, or the, the person eating any sort of seafood. So yeah, so that was sort of an outdoor exposure if you were dealing with leaching and vapor intrusion. And then the other, I kind of keep mentioning this, is that obviously we've got our own consumer products and household textiles that we have in our home or in an office, or wherever we are in indoor air. And so this is really, it's going to be an interesting problem once we start looking at VI, because typically you have to untangle what is the source, the PFAS source, and then what are you seeing in indoor air. And so that's been the long, drawn out question that we've been dealing with on non-PFAS sites. So now that we're thinking about, well, when we get to evaluating vapor intrusion, how are we going to do this when we have so many consumer products indoors, and compared to what you might have in your subsurface that might be volatilizing up. So just something to think about. Again, these are the same pathways: inhalation of particulates or vapors from household PFAS products and carpets, and then ingestion. You might touch a dusty surface, or your child might, and put their hand in their mouth, and so you have this incidental of the dust and any sort of particulates. And then dermal contact. Again, you could just be touching something, and maybe potentially that could be contacting your skin, and then you have exposure that way. So there's definitely a lot of things to consider when you think about vapor intrusion. Again, we're dealing with indoor sources as well as subsurface sources, and how do we untangle those. I think Ian mentioned he had a different study, but this is just out of the ITRC document. It's from the CDC data from 2022, and it's really just showing some of these longer chain PFAS and the biomonitoring that's been going on since about 2000, and this goes up to 2018. And really you're seeing, just due to lack of production, I believe, that there's a reduction in PFOA and PFAS blood lead levels. The purple is the PFAS, so that's quite a bit, big drop. But again, they're all sort of decreasing in their trend. So, okay, now we're at a question time. So Jennifer, I'll let you take over.
Okay, here we go. What type of PFAS is dominant in ambient and indoor air? Select one. So we'll just wait another, 15 seconds or so for people to vote. There's no, let's see. Looks like most people that are going to vote have voted. Now, Laura, this one I think actually has some technical content to it. So let's talk about what the answer is.
Okay. So the study that I showed, and kind of some of the previous work that was done on long range transport, shows that the fluorotelmer alcohols are the. Is that what you wanted me to do? Answer that question?
Yeah.
Or did I just give it away? Okay, yeah. So it was the fluorotelmer alcohols, the FTOHs. Just because they're volatile, they want to be in air, and they're lighter, and but they're not the. I mean, that's like a whole nother discussion with the ultrashorts. But yeah, in general, those are what they've shown. So.
Great. Okay.
Okay. All right. Are we back up and running? I can't really tell.
Yes, go ahead. All
right. Okay. So PFAS toxicology. I know Ian mentioned a bit about the research and development of toxicity values for PFAS is, I don't know if you're in the realm of toxicology, but it is going on at an astronomical rate. It is insane. And a lot of it is well-founded, right? We need to understand the toxicity of some of these, universe of compounds. So what I just wanted to point to really quickly, and this is more on the practical side. So Paracelsus said dose makes the poison, right? So as a toxicologist, you could overdose on water, right? It's but not all toxicity values that you see, let's say in the EPA RSL table, are the same. What happened in 2003, is that EPA came up with a tiered approach to toxicity sources, and they basically wanted to show, like, not all toxicity values studies peer review are going to be equal. So the tier 1 is kind of the gold standard. We call that the IRIS database, or the Integrated Risk Information System. And that is, it means that it has to go through EPA review, a very long public review comment period, typically, and that once it's established as an IRIS value, it becomes tier 1. It's usually very difficult to change that. Then we have tier 2, and those are from EPA's provisional peer-reviewed toxicity values, or PPRTVs, and those are established outside of IRIS. They're usually done, I would say, like 1-methylnaphthalene. They just came out with their PPRTV tox profile, and some of the studies, I would say, again, it's not the gold standard, but there are values out there. And then lastly, the tier 3, those are the other tox values. Those are, a lot of states are doing their own research. ATSDR, they have their own MRLs, which are the equivalent of, toxicity values that look at different dose, or acute and I think subchronic and chronic. So they have 3 different exposures, and then we have HEAST, which really hasn't been updated. It's the health effect assessment summary table, I believe. Used to be, it was EPA's, they used to update it quite regularly in the 90s, and then they just sort of stopped, or maybe they folded it into their PRGs. But anyway, so this is just something to note, that when you see a new RSL table, or a new RSL table comes out, and it says, the note says a state, or it says I for IRIS, then you kind of will know, oh yeah, that's just a little piece of information there. So I mentioned this before, the PFAS the toxicity values are coming at drinking from a fire hose, really. So the EPA RSL table, as I mentioned, is updated typically in May and in November of each year. And so starting back in November of 2014, that was when we first started to see PFAS, these substances on the RSL table. And really, what we were seeing were these oral RFDs. And so the RFD is the equivalent of the reference dose, which is the non-cancer side of things. So you're seeing a lot of oral RFDs, and then some changes here. And Jennifer, I know I have a PDF of this, so it's, I don't want to go into the details here, but you can just sort of see there's every 6 months, there's a lot of changes, with the exception of November 2022, there were no changes, which is kind of funny. But yeah, most recently we've got, now we've got some oral cancer toxicity values, which are labeled oral SFs, or oral slope factors. And that was based more recently in this past May. There's 6 PFAS that we do have some new values, and also they added in the new MCLs back in May. But anyway, the point here is just saying that there are 14 PFAS and their derivatives, which total 31 analytes that are in there right now. And in the fall, that'll happen again. There'll probably be some changes. So practical guide number, rule of thumb might be, if you're working on a site or you're trying to, understand some screening levels, you might want to consult the RSL table. One of the most interesting things that I want to mention here is that if you see, there is nothing that says inhalation. So currently, only the oral pathway is evaluated or have toxicity values for, which is interesting. And from a risk perspective, if you want to quantify risk from inhalation, you need an inhalation toxicity value. And the EPA used to allow you to sort of do this route-to-route extrapolation where you take an oral slope factor or an oral RFD and then you could turn it into an inhalation one, but they have since sort of decided that's not a great practice. Therefore, inhalation risk can't be estimated at this time, including from VI concerns, with the caveat that the next time EPA updates an RSL or you hear a study comes out, that might change. And when that does, when we have inhalation toxicity values, then yeah, we'll definitely be looking at VI and opening up that kind of floodgates to doing vapor intrusion work. So yeah, I know we only have like 15 minutes left. So the PFAS in indoor air, I showed you this earlier, this diagram that just mentions, all the different sources, and again, we mentioned this all, but what's interesting that they find is that both the volatile and non-volatile PFAS, that once they're airborne, but then they can settle into carpet and household surfaces, and you can really have a lot of, especially if you have young kids at home, in the carpeting, walking around or crawling around. So there's an exposure pathway there, but again, indoor air concentrations are typically driven by the fluorotelmer alcohols. This is out of the September 2023 PFAS guidance from ITRC, and it's just a study just showing composition in indoor air. This is in air, and you can sort of see, I color-coded some of these fluorotelmer alcohols, and you can sort of see that they're a bit higher than some of the other non-volatiles that are further on the left here. So that's just, again, that's in the PFAS guidance you can access online. Not so much with the subtle dust. It's sort of a mixed bag where you've got these fluorotelmer alcohols, they're kind of over here, and then you've got your more non-volatiles over here, but definitely you're seeing both in the subtle dust. So I believe my last section here is just talking a little bit about occupational air standards. So right now there are no PLs, there are no permissible exposure limits for PFAS. In fact, the OSHA acronym for PFAS actually stands for Personal Fall Arrest System. So they are like using an acronym that actually is for a different purpose. And then NIOSH, kind of similarly, they don't have anything, no recommended exposure limits, but they are they're doing research, looking at worker exposure and health assessments and toxicity testing, and especially looking at firefighting gear testing for PFAS. And then on the other side here, you've got the ACGIH, the American Conference for Governmental Industrial Hygienists. They actually do have some air threshold limit values, or TLVs. And again, they're very much looking into, I think everybody's working feverishly to update these lists for air standards for occupational, because a lot of times people are exposed, right, in an occupational setting if they're working with these consumer products. So yeah, there were 2 occupational studies that I just wanted to highlight. They really just looked at serum monitoring and air dust in the workplace, but maybe they caveat that by saying not necessarily in the breathing zone. And their focus was workers that were in the chemical production, you know, for PFAS chemical production or secondary manufacturing, baking PFAS on, firefighters, and then strangely ski wax technicians, because there's a high PFAS in those as well. So this is just the study, this one here on the bottom, the occupational exposure from 1980 to 2021. And you can kind of see they split out into different categories. The non-occupational populations, that's kind of all of, you know, the general public. And you can see those in the blue, and you can see really from a standpoint that general public is pretty much within, you know, I would say, you know, the one range of 1 nanograms per milliliter. And that obviously the higher the fluorochemical manufacturing workers, makes sense that they're going to be in the higher concentration range by orders of magnitude, 1,000, 10,000. And then we've got some other firefighters, first responders. But anyway, it's a really nice just kind of understanding about the range of serums that folks could be exposed to, just depending upon their occupational setting or whether or not they are exposed through their occupation. So that's it.
Great, thank you, Laura. So I guess a basic question would be, have there been documented studies that PFAS is in the soil vapor, like it is traveling in the soil?
I mean, from a physical chemistry perspective, I mean, it has, there's certain PFAS that would qualify based on the fact that they're volatile, considered volatile, and that's based on like their Henry's law constant, their vapor pressure. So yes, there is the potential that you would have that in, and I believe like there's some folks like Chase Holton, this is more in the VI realm, he has done quite a bit of work. He was working at Geosyntec for a while, but he was doing a lot of research on the physical chemistry and showing, yes, there is potential for these lighter phase. Like if you're thinking more of the, you know, the longer chain, you're probably not going to worry as much as you would about these, again, these shorter chains, including the ultra shorts.
Right, yeah, there's lots of overlap between those two topics today. So let's see, how about, yeah, so our blood and our bodies. So we are able to secrete some of these chemicals, but not maybe as fast as we're gaining them in our bodies, or how do we have to worry about like increasing, or
you mean bioaccumulation? Because that's where yeah, oh yeah, absolutely. I think Ian even had this like great graphic that showed like bioaccumulation, and you know, they all have the ability to bioaccumulate. When I was showing that serum trend where it was going down for the PFO and the PFAS, I think the thought was that it had dropped in the last 20 years because that was right about when these longer chain chemicals were being taken out of the consumer, you know, consumer products. So there is the ability over time that we're not exposed. So there is good news there, right? So as things are removed from our consumer market, that is definitely what we're thinking is happening. I don't know if I answered the question.
Yeah. So the ultra shorts, are they in the TFAs that Ian was talking about? Are they in indoor air and at concerning levels?
I would say most likely. I don't know specifics, but you know, if they're in a consumer product that is coming into your house or into your office place, which I'm assuming you are, or in, you know, applications of, I was going to say pesticides, that there's definitely potential for that as well. But again, we're thinking about this in a theoretical way because we are not able to quantify risk as of yet, because we don't have any inhalation toxicity values available yet. But I have a feeling this will all change. And when it does, it won't just be that we have a pathway of vapor intrusion, which means something below a building is getting pulled into that building because the building's got an HVAC system that's running. But it's going to be, is the exposure from our consumer indoor air, things that we buy and put in our home that are off gassing. I don't know if that's the technical word, but they're volatilizing off into the air. Is that, that in and of itself is one source, but then the source that we're worried about more in this vapor intrusion realm is coming from the subsurface. So kind of untangling those two will be interesting.
Yeah, this is reminding me, so I'm old enough that back when I was working in consulting, if there was, solvents in the groundwater, we didn't really worry about them because if you were in an area where people weren't drinking the groundwater, we just didn't really worry about solvents in the groundwater. But, then we learned about vapor intrusion. And so far, I think with PFAS, we've been like, oh, well, people aren't, if we're not, we provide them with drinking water from the public supply or from, we don't have to worry about the PFAS in the groundwater if we can give people an alternative water supply. So maybe we're back in that situation again where, we thought we didn't have to worry about it, but maybe we should.
Yeah. And the VI mitigation in and of itself, let's say there are PFAS concentrations for chemical X that do have inhalation toxicity values and we're screening it and we're exceeding, then it would just fall back into the same category of what would be a vapor mitigation system, which are typically like you put in like a subslab depressurization system, or you put in like a coating, something to keep the vapors from getting inside. So we have all the tools to mitigate vapor intrusion, but it's just, like I said, the more kind of philosophical question is how do you separate out what would be coming from the subsurface versus what's coming, how are you exposed from indoor air, right? Because the indoor air you most likely brought in yourself.
Right. So I think we'll have to end on this question, but so, we've talked about there's not regulatory levels for PFAS in air, there aren't toxicity levels, but are those coming? Are people studying them? Do we anticipate they're coming soon, and for, certain chemicals or the shorts or the longs, or what are we thinking?
Well, that's a really great question. That's like the $1 million question. I would say, keep an eye to these RSL tables. Keep an eye to, if you're worried about vapor intrusion from PFAS, like I said, as I started my talk, everybody asks me like, hey, because I kind of on both, overlapping the vapor intrusion and PFAS, but I don't know. I mean, I have to say that we're thinking about triaging, right? So they were thinking we need to do oral toxicity first because that's where we're worried about people drinking groundwater, drinking, these things that are the main concern or the risk driver. So to be honest, I don't know, but I wouldn't be surprised if, in the next 6 months to a year, we start seeing inhalation toxicity values, and they may be coming from, again, this may not be a tier 1 IRIS number. It might be tier 2, a PPRTV from EPA, or it might be tier 3, probably most likely tier 3, where it's coming from a state. Thinking California, I know Wisconsin has a bunch of toxicity values that they promoted. So yeah, I guess it's coming, but I just don't know when. And it would be for the more volatile components that, the shorter chain, things that are considered volatile that are probably already in the RSL table.
Right. All right. Well, both of these topics leave me a little feeling not as optimistic. Yeah. Oh my gosh. That's so much to worry about and think about, but it seems like there's definitely things that can be done on both sides. Quite a few questions were coming in as well about just the consumer products and the things we have in our homes and using them and worrying about them. But we just have to work on, as one of my directors always says, first thing you got to do when the bathtub is overflowing is turn off the water. Like, we need to get these things out of commerce, but we'll be dealing with the after effects for quite a while.
There's definitely a lot of progress on that side too. I mean, that's you know, you probably know all about it with TRI. Things are reportable now, and you know, we've got you know, CERCLA is designated hazardous, not, you know, so there's movement for sure in that direction, but
right.
I'm just like, I'm like the don't shoot the messenger. I'm just.
All right, well, I'm going to just plug a couple of related webinars that we have coming up that Ian and Laura touched on. So we are going to have one with the state of Maine folks talking about agriculture and some of the studies that they've done up there about plant uptake, not of the ultrashorts, I don't think, but of other PFAS. So that one is going to be coming up, I think, November 6th. And we've got one that's going to be focused on skiing and ski wax and exposure and things for skiing specifically. And that's going to be, it's looking like October 16th. So I should have more webinars put together, and you'll be getting email with more information about future webinars, but plug those. So thank you very much to Laura and Ian. I think Ian had to jump off because he's a busy person. But thank you so much to Laura for joining today, and Ian. And I will end this webinar, and thank you to everybody that attended. Hope you enjoy the rest of your day. Bye-bye.
Yeah, bye.